Swayam Prabha. Digital India. Educated India.
Welcome to lesson 4.10, design of bituminous mixes part 2. This is the second part of the presentation on design of bituminous mixes, and as you recollect that this is a part of module 4, which is on pavement design. The main objective of this lesson is to make the student learn about Marshall method. In fact, in the previous lesson on bituminous mix designs part 1, we have covered various aspects such as what are the important parameters that are to be considered in designing mixes, what are the requirements of mix design, and we have also identified that air voids, which is a volumetric parameter of bituminous mix, is one of the most important parameters to be considered in designing the mixes. And mix design is a process in which we have to identify a proper aggregate skeleton structure, because mix after all consists of aggregates of different sizes and bitumen or any bituminous binder as binder and compacted. So, we have to find out the optimum combination of aggregates and binder. We also have to find out what is an appropriate aggregate skeleton and also the type and then content of the bitumen that we are going to use. And of course, we have to also think in terms of what is an appropriate compaction effort to be used for preparing the specimen and then for testing and evaluating them. So, we would like to discuss Marshall method of mix design, which is the most commonly used method for designing bituminous mixes. Also learn about the selection of optimal proportions of different components of mixes, what should be the guidelines that we should adopt in selecting optimum bitumen content, having selected what is an appropriate aggregate skeleton, aggregate gradation, and it is also expected that the student would be able to understand the significance of various test conditions adopted in the mix design procedure, because we are going to test bituminous mixes and then find out various parameters. So, these tests are going to be conducted under various conditions. So, what is the implication or significance of these different conditions, how they are correlated to the actual conditions, and what is the influence of these parameters on the performance of these mixes will be understood. As I indicated, there are various methods of designing bituminous mixes. A few common methods are Marshall method, this is the most commonly used method, film method, and superpave mix design method. Superpave, as I indicated in when we are discussing bituminous binders, refers to superior performing pavements. This is of a more recent development. All these mix designs mainly involve preparation of laboratory trial mix specimens. That means, a number of specimens would be prepared with various combinations of aggregates and binders, and all these specimens will be tested, and then on the basis of the results that we obtain on these trial mixes, optimum combination of binder and aggregates will be selected. Marshall method of mix design was developed by a gentleman named as Bruce Marshall, in the late 30s for the Mississippi Highway Department in the United States. Ministry of Shipping and Road Transport Highways recommends that the Asphalt Institute procedure manual MS2 should be followed for design of mix designs, bituminous mixes. So, most of the provisions that we are going to discuss in terms of Marshall mix design will be as per Asphalt Institute procedure. The original procedure for designing bituminous mixes that were originally developed by Marshall, especially in terms of the compaction effort used, underwent lot of changes over all these years, so that the mix design corresponds to the actual conditions of traffic, different climatic conditions that are prevalent now. So, the mix design procedure now we are now adopting is expected to be simulating different traffic conditions and also various climatic conditions. And the Asphalt Institute MS2 mix design guidelines are mainly meant for dense graded bituminous mixes. The main steps involved in Marshall mix design method are selection of mix type. We have to first identify what is the type of mix that we are trying to design. Is it the bituminous concrete, is it dense bituminous concrete, or any other type of mix. So, obviously, we will first try to identify whether am I trying to provide a dense graded mix, am I trying to provide a gradation which has got more coarser fraction, am I trying to design a mix where only the surface characteristics are important, I should get good surface characteristics, or I am designing a mix where rutting is a major problem because of high temperatures, heavy loads. So, according to the requirement, we have to select what is the type of mix that we are going to select, and having done that, we will select what is the maximum aggregate size and select an appropriate aggregate gradation. Maximum aggregate size, as we indicated earlier, will be selected on the basis of the thickness of the layer that is going to be provided, and the aggregate gradation, usually most agencies have a specified gradation given for each mix. So, normally it is expected that those are to be followed unless it can be shown that deviating from the gradation specified is for good, and if you can convince the agency, then you can go for other gradations other than what has been specified by either MORTH or other gradations. The minimum layer thickness is usually more than 2 to 3 times the maximum aggregate size. This is just to give you an indication of what can be the maximum size of aggregate that you can use. It is a function of thickness of layer that we are going to provide. Similarly, the aggregate fractions are usually designated as coarse, fine, and then filler. Coarse is an aggregate that is retained on 2.36 millimeter size, fine aggregate passing 2.36 millimeter size and retained on 75 micron sieve. Mineral filler is that which passes 75 micron sieve. The next step that we follow in Marshall mix design method is the selection of binder, that is type of binder also has to be selected. We had in the earlier lessons given guidelines of what is the type of binder to be selected for different traffic conditions and for different climatic conditions represented in terms of what is the maximum temperature and also what is the minimum temperature. So, we know how to select an appropriate grade of binder for different situations. After selecting the binder, we also have to select the aggregates. There are specifications available for what is the quality of aggregates that we have to use for different types of layers. If an aggregate is to be used in surface course, it will have to satisfy different requirements. If it is used in a binder course, its requirement will be different. So, we have to select binder and aggregate satisfying the requirements for a specific project and for a specific layer. So, these are to be selected on the basis of the traffic and climatic conditions, and these metals have to be tested for the source properties. As soon as we get these metals from source, normally these are tested, and once they are satisfied, subsequently they may be tested at regular intervals. The next step is to select design aggregate gradation considering the traffic and climatic conditions. The next step is preparing test specimens of bituminous mixes using the aggregate gradation that is selected and the binder that is selected with appropriate compaction effort. We also have to select what is an appropriate compaction effort. Ministry of Shipping and Road Transport suggests a specified compaction effort as per a specified procedure for all highways. So, we expect for all highways we are talking about heavy traffic volumes. So, we are talking about compaction that is produced by heavy traffic over some period of time. So, we are talking about heavy compaction. So, that is what we are going to discuss about. Rather, all the specifications of Ministry of Shipping and Road Transport and Highways is based on heavy compaction effort. But if we are designing mixes for roads having very low traffic, so we can go for smaller compaction efforts. So, the corresponding equipment, the corresponding compaction effort also can be used and the mixes tested corresponding to that compaction effort. So, we also have to select a compaction effort. Then those specimens that are prepared will be tested. We have to make number of additional trials if the initial trials that were made when these specimens are tested, they do not yield required properties or they do not satisfy the specifications that are meant for a specific mix. Then the next and then final step, rather the final step would be the selection of optimum binder content as per the specified criteria. How to select the optimum binder content, what is the criteria to be adopted for selecting the optimum binder content also is usually specified in a given design procedure. So, these steps include grading of commercially available mineral aggregates, because we are not going to have aggregates crushed and then sieved as per individual sieves. We are going to get aggregates either 20 millimeter aggregate, 12 millimeter aggregate, stone dust or whatever manner it is supplied. So, we would select appropriate sizes of aggregates that are available, aggregates that are suitable, having suitable quality. Then those aggregates will have to be blended as we have discussed in the previous lesson. So, the proportioning of mineral aggregates will have to be done by blending. Then we have to find out the specific gravities of the binder and the aggregates. The specific gravity of binder can be determined using a pyknometer method. The specific gravity of aggregates have to be determined for their bulk specific gravities and also for the apparent specific gravity, though normally apparent specific gravity is not used in mixed design. Then we have to prepare Marshall specimens, because we are talking about Marshall method of mixed design. Then using the aggregates that are selected, after blending the aggregates, so we mix the aggregates in the blending proportion that we arrived at, then that should give you a grading that is within the specification limit. So, using that blended portions and the binder that was selected, they have to be taken together and then Marshall specimens are to be prepared, and these Marshall specimens are to be tested for the bulk specific gravity. Marshall specimen is nothing but adding aggregates and bitumen together and compacting them. These specimens are to be tested for their bulk specific gravity of the compacted specimen. They have to be tested for stability, they have to be tested for flow, and we also have to find out the specific gravity of the loose mix. We have discussed in the previous lesson terms such as voidless volume of mix, which would give you GMM, which is the maximum specific gravity of the loose mix. These are the parameters that we have to measure. So, using this information, we can calculate the air void content in the compacted mix, we can calculate the percentage voids in the mineral aggregate filled by binder or bitumen, and using all this information, we can also calculate other volumetric parameters also. Using all this information, we will select an appropriate binder content known as optimum binder content. Then we will check at this optimum binder content, what are the various parameters the mix will have in terms of strength, in terms of flow, in terms of various volumetric parameters. So, at optimum binder content, what are the properties this mix is going to have? Those properties have to satisfy the specification that are given for given mix. For testing the samples, we have to determine the bulk specificity of the specimens. Once we compact the specimen, prepare a specimen by adding aggregates and binder together and compact them, and then we have a specimen prepared. That compacted specimen has to be, its bulk specific gravity has to be determined, and all these specimens will have to be conditioned by keeping them in a water bath and maintained at 60 degrees centigrade for a period of 30 to 40 minutes duration. Basically, the idea is to test the specimens at a temperature of 60 degrees. For this, we have to condition these specimens by putting them in a water bath. This is the way how it has to be conditioned, which is maintained at 60 degrees. The conditioning has to be done for about 30 to 40 minutes. These conditioned specimens will have to be tested in a Marshall testing apparatus for determining the stability and flow of each one of these specimens. The stability values have to be corrected for non-standard height or volume. We will discuss about what are the standard dimensions of the specimen that we are expected to maintain in terms of its diameter and also in terms of the height that is expected to be attained. So, we are talking about a standard size specimen, but it is not always possible to get the same height because of the compaction effort that we put and also because of the mass of the total aggregate and binder that we take. So, we may get different heights. So, the volume of the specimen is going to be different. So, as the volume differs, the stability value that we attain in the Marshall testing machine will have to be corrected to correspond to a standard volume. There are correction factors available that can be done. Then the test should be completed within 30 seconds after removing from the water bath. This is to ensure that the temperature does not fall below 60 degrees centigrade. There should not be any significant difference. So, we should not wait for 2 minutes, 3 minutes before the test process is completed. As soon as the specimen is removed from the water bath, which is at 60 degrees centigrade, the test should be completed quickly. The standard Marshall method involves preparing a 4-inch diameter specimen, 102 millimeter dia, and 2.5 inch height or thick specimen, which is about approximately 64 millimeter height, of bituminous mix with a selected gradation of aggregates and a binder content. We already discussed we are going to select a gradation aggregate gradation and also binder type and then certain binder content. So, with this combination, with the compaction effort that we produce adopt, we should be able to produce 4-inch dia specimen and having a height of about 2.5 inches. The standard compaction effort used is by dropping a hammer of 4.5 kg, 10 pounds, mass through a free fall of 457 millimeters, that is 18 inches. So, the compaction effort adopted is the compaction is done by using a compaction hammer, Marshall hammer, weighing 4.5 kg and falling from a height of 457 millimeters. The maximum size of aggregate that we can use, because we are using a 4-inch dia specimen. So, normally the maximum size of aggregate that we can use is 1 inch or 25.4 millimeters. But if we want to test an gradations, mix having a gradation having a larger size more than 25.4 millimeters, some of these mixes have got more than 30-40 millimeter size. So, if you want to test those mixes, you have to prepare larger size specimen. Normally 6-inch specimen also can be tested. We have to prepare a series of test specimens with the selected aggregate blend and with different binder contents. So, we will keep the aggregate gradation fixed, the blend fixed, but we will go on varying different binder contents. So, for each binder content we will prepare number of samples. So, we will have specimens prepared at varying binder contents. Then we can find out what is the effect of varying binder contents on various mix parameters, and then select one of these binder contents or any optimum binder content which gives us optimum performance. this selection of initial trial binder content, if you do not have an idea of what could be the range within which optimum binder content is going to lie, the selection can be made as P equal to 0.035 multiplied by A plus 0.045 multiplied by B plus capital K into C plus F. P is the approximate binder content, this is expressed as the percentage by weight of total mix, whereas A is the percentage of aggregate retained on 2.36 millimeter sieve, B is the percentage of aggregates passing 2.36 millimeter sieve and retained on 0.075 millimeter sieve, C is the percentage of aggregate passing 0.075 millimeter sieve, K has got different values 0.15, 0.18, 0.20 for various percentages of filler, which is the material passing 75 micron sieve. For example, if the filler content is 11 to 15%, the value of K is taken as 0.15. If the filler content is less than 5%, the value of K is taken as 0.2. F is a value that is to be selected on the basis of the assessment of absorption by aggregates of bitumen. So, what is the expected quantity of bitumen that is going to be there for in the aggregate pores. So, if you know the absorption of aggregates, so the F can vary from 0 to 2%. Completely non-absorptive aggregates, we can take a value of 0, highly porous aggregates, a value of 2 can be taken. The initial binder content is normally assessed on the in terms of the film thickness that is required depending on the gradation. So, depending on the size of particles that we have, percentage of different fractions, what is the surface area can approximately be calculated, and what is the minimum thickness of binder that has to be there coating these aggregates from the point of view of durability of these mixes can normally be assessed. So, normally the initial trial binder is on the basis of the film thickness that is required to coat these aggregates, and also taking into consideration if these aggregates are absorptive, then some amount of bitumen is going to go into these pores. So, taking into consideration there is this is an empirical formula, obviously this will serve only as an initial trial thickness. So, we can take this binder content rather initial trial binder content, you can start with this binder content and select other binder contents on either side of this. Normally specimens are to be tested or prepared at 6 different binder contents, and at each binder content normally 3 specimens are to be prepared. So, if you take about 25 kg of blended aggregate and about 4 liters of binder, that would be normally be sufficient to cover this 6 binder contents and 3 specimens at each binder content. Before we go about preparing these specimens, we have to determine the viscosity of binder at different temperatures using rotational viscometer. We discussed about Brookfield viscometer in the previous lessons, and then measuring absolute viscosity using rotational viscometers. So, we have to determine the viscosity of bituminous binder at various temperatures. This exercise is necessary to select the mixing and compaction temperatures. We will see how. There are guidelines that are available about what is the consistency of the binder that we should adopt for compaction process, what is the consistency of the binder that is to be adopted for mixing the aggregates with binder. So, the specifications are, as you see in this sketch, for mixing typically the viscosity should be ranging from 0.17 plus minus 0.02 Pascal seconds. Similarly, the viscosity range for compaction is 0.28 plus minus 0.03 Pascal seconds. For example, if you typically have a plot between temperature and then viscosity on y axis given by this line, okay. So, you can select what is the range within which mixing can be done, range within which this requirement is satisfied. So, these temperature range can be selected. Similarly, what is the range within which compaction can be done given by these 2 temperatures. So, this is normally how we select the range of temperature for mixing and also the range of temperature for compaction operation. For preparing the specimens, the compaction of loose hot mix, obviously we have to add aggregates and then binder and then heat it to the temperature that we have just indicated, and then that loose mix will have to be compacted so that we get standard test specimen dimensions. The mixing temperature corresponding to a viscosity of 0.17 Pascal seconds. Similarly, the dry aggregates are heated to a temperature not exceeding mixing temperature plus about 28 degrees centigrade. The binder should be heated to mixing temperature, which would be different for different types of binders, because those viscosity ranges are attained at different temperature ranges for different types of binders. The binder plus viscosity, binder plus aggregate mix is placed in the compaction mold, which are to be preheated, and the loose mix, heated mix is compacted. The compaction of loose hot mix to obtain a test specimen of standard dimensions, as we indicated just in the previous slide. Standard compaction effort used is by a 4.5 kg hammer having a free fall of 457 millimeter. The maximum size of aggregate that we can use is 25.4 millimeter. For larger size of aggregates, we can also use 6-inch dia molds. On the left hand side, you see typically a sketch of specimen that we are trying to prepare, and this is the mold that we are using, and this is the loose mix that we have placed here, and this is the pedestal of the hammer, and this is the mass that is going to fall from a specified height. Hammer is not seen here. So, we have the hammer here, and this is the height of fall that we are going to get, and below this there is a base plate. Yes, we see the hammer here now. So, we also see the height of fall. So, the hammer will be lifted up and allowed to drop freely, and this exercise is repeated number of times. You see two different photographs of an automated Marshall compaction equipment. On the left hand side, you see that hammer, this is the hammer, and this is an arrangement using which you can set the number of blows here that you want to apply, and then the hammer gets lifted up and then repeatedly dropped, and this is where the mold is fixed. This is a manual Marshall hammer, and these are molds, base plate. Typically, for preparing the specimen, MORT specifies for heavy compaction 75 blows are to be applied using Marshall compaction hammer on both faces. First, you have to compact it on one side, then the specimen has to be reversed, then again 75 blows of Marshall hammer have to be applied on the other face also. So, this is the standard compaction that is recommended for all the mixes that we use for highways. So, the specimens that are compacted will have to be extracted from the mold. Of course, before that we will have to determine the specific gravity of aggregates and also binders, and the specimen that is extracted from the mold, we have to find out its bulk specific gravity of the compacted mix, that is GMB, which this is obtained by measuring the dry mass of the mix. You take this dry mass of the specimen and find out the volume of water replaced by the saturated surface dry specimen. The specimen has to be saturated, then the surface water has to be removed, and its weight has to be taken, and then its weight in air has to be taken. The difference in weights will give us the volume of water replaced by saturated surface dry specimen. So, the dry mass of the specimen divided by volume of water replaced by the saturated surface dry specimen, which is nothing but the bulk volume, gives us bulk specific gravity of the compacted mix. Then the specimen is put in a Marshall testing machine and Marshall test is conducted. Marshall test is nothing but these are breaking head put on both sides of the specimen. This is specimen. So, a compressive load is applied along the diameter of the specimen at a rate of 51 millimeter per minute. We know that the temperature of the specimen is going to be maintained at 60 degree centigrade. The inside radius of the breaking head is going to be approximately equal to that of the specimen, which is 51 millimeters. So, load at this rate is applied. What we observe is the load at which the specimen breaks. So, either in a proving ring or in a dial gauge or in any automated measurement, we see the load increasing. Then after certain stage, once the specimen fails, the load starts decreasing. So, we have to observe what is the failure load, and we also have to observe what is the deformation that this specimen undergoes when the specimen fails. What is the starting from the initial deformation of 0, the deformation at failure condition has to be observed. So, the breaking load is known as stability and the deformation at failure is known as flow. So, these are known as Marshall stability and Marshall flow. This is an automated Marshall testing machine which uses LVDTs and load cells to automatically measure the load and the corresponding deformation, and it can automatically record it into a computer. Of course, we can use other simple equipment also. This is a water bath which is used to maintain constant temperature. The stability that is obtained from Marshall testing machine, as I said, are to be corrected for non-standard volume. If the standard is if the dimensions attained are 4-inch dia and then 2.5 inch height, there would not be any correction that is required, but if mostly the height varies, there is certain correction that is to be applied. For example, if the volume is within 509 to 522 cc, there would not be any correction, but if it is more, the stability will be reduced. If the volume is less, the stability will be increased. After the Marshall test is done, we will have to carry out volumetric analysis. This is to estimate important volumetric parameters such as air void content, voids in mineral aggregate voids filled with bitumen, and so on for each of these specimens. And for each binder content, we have to determine the maximum specific gravity. This is voidless specific gravity of the voidless loose mix. This has to be determined, and using all this information we calculate the effective specific gravity of aggregates and carry out the volumetric analysis to compute air voids, VMA and VFP. A typical example of volumetric analysis is given here. For example, if we have the initial data wherein we have taken 3 different sources A, B, C of aggregates, and they have been blended in, let us say, this proportion 25%, 45% and 30% to obtain the desired gradation, and the bulk specific gravity of source A, B, C and are 2.954, 2.896 and 2.835 respectively. These have been measured. So, the bulk specific gravity of the combined aggregate will be 100 divided by 25 is the proportion of aggregate A in the blend divided by the corresponding bulk specific gravity 2.954 plus 45 by 2.896 plus 30 by 2.835. So, the bulk specific gravity of the blended combined aggregate is 2.8915. Let us say we have added 5% bitumen by weight of the total mix, and the specific gravity of the bitumen was measured as 1.03 GB. Bulk specific gravity of the specimen, this is one specimen that we are talking about, we have measured the bulk specific gravity of the specimen, that is 2.552, and maximum specific gravity of the loose mix for 5% binder content is 2.729. So, the effective specific gravity of the aggregate GSE, which is calculated taking into consideration all the voids except those that absorb bitumen, given as PMM minus PB divided by PMM by GMM minus PB by GB, where PB is the proportion of binder, GB is the specific gravity of binder, GMM is the maximum specific gravity of loose mix, PMM is the percentage of total loose mix, this will of course be 100. So, 100 minus 5 divided by 100 divided by 2.729, that is the maximum specific gravity of loose mix for 5% binder, minus 5 by 1.03, this gives us 2.9884. The maximum specific gravity of loose mix for other binder contents can be determined by preparing specimens at other binder contents, but if that has to be calculated on the basis of what has been determined for one binder content. So, this expression can be used to calculate the maximum specific gravity for of loose mixes for other binder contents, given by GMM equal to PMM by PS divided by GSE plus PV by GB. For example, for 6% binder content, 100 by 94 divided by 2.9884 plus 6 by 6 is the binder that we are referring to, divided by 1.03. So, that is about 2.6823. The bitumen absorption, we can compare this with the specific gravity that we obtained for 5%, 2.729. Bitumen absorption for 5% binder content case can also be calculated using this expression, that is 1.155%, and the effective bitumen content after deducting the bitumen that has gone into the surface pores of aggregates can be calculated using this expression PB minus PBA into PS. PS is the proportion of aggregates divided by 100. So, 5 minus 1.155 is the percentage of bitumen that is absorbed, into 95 is the proportion of aggregates divided by 100, that is about 3.9%. So, we have put 5% bitumen, but 3.97% is what is available to effectively coat the aggregates. Then we calculate the voids in mineral aggregates using the expression 100 minus GMB into PS by GSB. So, it works out to 16.15%, and air void content using specific gravity of loose mix and bulk specific gravity of the compacted mix. So, GMM by minus GMB by GMM expressed as percentage. So, air void content in this case for this specimen worked out to be 6.49%. Voids filled with bitumen is nothing but total voids in mineral aggregate minus air void, rest is bitumen. So, VMA minus VA divided by VMA expressed as percentage. So, this is working out to 59.81%. So, we have let us say approximately about 6 binder contents. For each binder content we have about 3 specimens. So, we can take average of those 3 specimens. So, basically we have all results for 6 different binder contents. So, we have to select an optimum binder content that is giving us satisfactory properties. This can be selected by observing various mix parameters with binder content. What we normally examine is how stability varies with binder content, how flow varies with binder content, how the unit weight of the total mix varies with binder content, what is the variation of percentage of air voids, variation of percentage voids in mineral aggregate, variation of percentage voids in filled with bitumen. Typically, this is the trend that we expect to get in terms of stability as binder content varies. It is normally expected to initially increase and reach a peak and then start decreasing afterwards. Unit weight also is expected to display similar trend. It will start increasing initially because of the increased density that is made possible by reorientation of the particles which are lubricated by the binder. but subsequently once it attains its densest position, any addition of binder having low specific gravity is only going to decrease its unit weight. So, you should we can expect that unit weight is going to decrease after some binder content. So, we are normally interested in binder content that give us maximum unit weight. We are also interested in binder content that give us maximum stability, but they may not exactly coincide, and this is how the flow is going to increase. As you go on increasing the binder content, typically the flow is going to increase because of increasing binder contents. So, we normally have specifications in terms of a range of flow, and this is the corresponding range of binder content within which the specified range of flow is satisfied, and this is how the air void content is going to be varying with binder content. As the binder content is increased, air void content is decreased. So, in the case of air void also, the specification will normally be in terms of range, and we can identify what is the corresponding binder content within which the given range of air void contents can be obtained. And voids in mineral aggregate typically usually start decreasing and then start increasing. It is not necessary that in all cases you exactly get a similar shape. So, once you get this shape, depending upon where the minimum of VMA specification is, whether it is here, here, there. So, accordingly we can identify what is the binder content that can be selected. Similarly, voids filled with bitumen, these are voids in mineral aggregates that are filled with bitumen. So, as the binder content increases, the voids filled with bitumen will go on increasing. So, the specification for this will also be available and the corresponding binder content can be identified. So, for selecting the optimum binder content, we normally have to select a binder content that satisfies all the mix requirements, that is specifications given by a given agency. These are to be selected. The specification should normally be developed on the basis of performance of mixes under specified conditions. So, we believe that whatever specifications are given by MORTH or Asphalt Institute or other agencies are on the basis of observation of the mixes and about their performance under varying conditions. The Asphalt Institute's main criteria for selection of optimum binder content is a median value of 4% air void content. So, the binder content that gives us 4% air void content is the optimum binder content, provided it satisfies all the other requirements that are given. If it does not satisfy any particular requirement, we can make slight adjustments to the binder content that we obtain for 4% air void content. These are the Ministry of Shipping, Road Transport and Highway specifications for heavy traffic. The number of hammer blows that are to be applied in preparing a specimen on each face of the specimen are 75 blows. The minimum Marshall stability that has to be attained is 900 kg. The Marshall flow should be ranging between 2 to 4 millimeters. The air voids in the compacted mix should be ranging from 3 to 6%. The voids in the mineral aggregates VMA percentage, which is calculated which is based on maximum size of aggregate. We have different specifications for different maximum aggregate size. This information I put in the next slide. Voids in the mineral aggregates filled by bitumen range from 65 to 75, and the retained stability on immersion in water at 60 degrees centigrade should be minimum of 80 degrees centigrade. This is a test that has to be conducted, the retained stability test on immersion. This has to be conducted to assess the damage that could be caused to the mixes when it is subjected to moisture, especially in locations where you have heavy rainfall, and also when you are using aggregates that are likely to strip. So, we are concerned about the loss in stability because of moisture. So, what we do in this test is we test normal specimens which are conditioned to normal testing procedures, say 30 to 40 minutes, and we also prepare a separate set of specimens and put them in water bath for longer periods, specified periods at 60 degrees centigrade, and then test them also and find out the Marshall stability of those specimens also, and compare the unconditioned specimens and conditioned specimens and see what is the loss in Marshall strength. So, they should have a minimum of 80% of retained Marshall stability. This is the criteria for minimum voids in mineral aggregates depending on nominal maximum aggregate size. For example, for 9.5 millimeter nominal maximum aggregate size, and also depending on the targeted air void content. If you are targeting an air void content of 3% for 9.5 millimeter aggregate maximum size, 14% is the minimum voids in mineral aggregate that has to be provided. As you see, for smaller aggregate size, the voids in mineral aggregates are specified to be larger, because we have to put more bitumen into the mix. So, we have to create more voids in the mineral aggregate, so that we can put more bitumen. More bitumen is required for smaller size of aggregates, because this surface area is going to be more. So, the binder that is required to coat the smaller size fractions will be larger. That is why we have to create more voids in the mineral aggregates, so that we can put more bitumen there. On the other hand, when you consider larger size aggregates, for example, when you see 25 millimeter size and we are trying to create, let us say 3% air void content, then the minimum VMA is less than what we consider for smaller size aggregates. Those are the specifications that we consider as for MORTH for normal mixes, but as per IRC special publication 53 2002, which deals with specifications of bituminous mixes with modified binders, polymer modified, rubber modified, and various other types of modified binders. The number of hammer blows is of course 75 only, and these are the parameters that we consider, and the requirements for various climatic conditions: hot climate, cold climate, high rainfall area. The minimum stability for hot climatic conditions is 1200, cold 1000, and again if it is a high rainfall area, we have to have a minimum of 1200 kg minimum stability. Flow range is 2.5 to 4, 3.5 to 5, 3 to 4.5. Similarly, there is another parameter that is considered, which is called as Marshall quotient, which is nothing but Marshall stability divided by Marshall flow, which should range between 250 to 500. Retained stability requirement is also there, minimum of 90%, 95%, 100%, and air void requirement is 3 to 5%. Normally, the binder content, as I indicated, will be selected either corresponding to 4% air void content, and that is the optimum binder content if it satisfies all the other requirements, or on the other hand, we can also examine the binder content range that satisfies all the criteria. For example, if stability, if this is the acceptable range for minimum stability, on this side of the binder content you will have low stability, on this side of the binder content you will have low stability. So, this is the range within which we get acceptable stability, and this is the binder content, range of binder content within which the flow is going to be satisfied. This is the binder content range within which air void content specification is going to be satisfied, and let us assume in a given case for all binder contents VME is satisfied, and more than this binder content is required to have the VAB consideration satisfied. So, from this we can identify this is the range of binder content which satisfies all the requirements. So, possibly you can select the midpoint of this as your optimum binder content. The main advantage of adopting Marshall mixed design method is it is relatively inexpensive especially when we are comparing this with more recently developed SuperPay mixed design procedure. This is convenient for design and also for quality control. We can have a Marshall mixed equipment kept in field laboratory also. Even the compactor can be taken to the field, and then mixes can directly be collected from field. and then compacted there itself, then the specimen can be brought to the laboratory and then tested. So, it can be considered to be a convenient method for field quality control also and for laboratory testing also. Lot of importance is given to air void in this mix design method. As we already established earlier, air void content is a key parameter towards the performance of the payments. It also accounts for the strength and durability requirements of the mix. It can be used on site also, but the limitations of this method are, this is an impact method of compaction. So, it does not really simulate what is happening in field. There is some kneading action that is taking place. So, that is not exactly simulated in this impact method of compaction. It does not consider the shear strength in the method of testing the specimen, which is diametrical loading. It does not take into account the shear strength of the specimen, because the load is perpendicular to the compaction axis. Marshall test data cannot normally be able to predict fatigue and permanent deformation behavior of in service payments. This method also does not give proper guidelines for selecting the quality of bitumen. The laboratory mix design, that is aggregate, gradation, optimum binder content and the corresponding mix parameters like stability, density, air voids, etc., is normally considered as the target to be attained in the field within permissible tolerances. Whatever is established in the laboratory and you say this is the binder content and these are the corresponding properties that we obtained in the laboratory, these are to serve as target values to be checked for in the field. MO and TH specifications refer to mix parameters to be attained after several years of traffic. Normally, if we start with 6 to 8% initial air void content, this is soon after compaction, initial compaction, that should be considered to be okay, assuming that a minimum of 98% laboratory density is attained. Normally, the specification is that whatever is the laboratory density that you obtain corresponding to optimum binder content, at least 98% of that should be attained in the field. So, if you can maintain about 6 to 8%, assuming that we are getting only 98% in the field, so that would correspond to 100% compaction of about 4%, which you expect to be attained after several years of traffic. So, we are starting with the initial of 6 to 8, we expect that there is going to be some secondary compaction, say about another 2%, 3%, then the air void content after several years can get reduced to, let us say 3 to 4% or 2%. So, which should be considered to be an acceptable thing, but if it gets reduced further, that is a problematic mix. To summarize, in this lesson we learnt about various steps involved in the Marshall method of mix design. We also discussed about the preparation and testing of specimens of bituminous mixes. We also discussed how various parameters vary, various mix parameters vary with binder content, and also discussed how to select optimum binder content on the basis of Marshall test results. Let us take a few questions from this lesson. What does the compaction effort used in preparing Marshall specimens correspond to? Why are the Marshall specimens tested at 60 degrees centigrade? Estimate the air void content in a specimen if its bulk specific gravity is 2.50 and the maximum specific gravity of the loose mix is 2.60. What are the advantages and limitations of using Marshall method for designing bituminous mixes? Now, we will take up the answers for the questions that we asked in lesson 4.9. This was part 1 of bituminous mixes or design of bituminous mixes. What are the main modes of failures of bituminous mixes? Bituminous mixes normally fail in various modes, one of them being cracking of different types, cracking that can start from bottom up cracks, cracking that can start from top down cracks caused by various reasons, repeated application of loads, climatic conditions, cyclic variation of thermal stresses. Various parameters can cause cracking of these mixes. They can be starting from bottom, they can start from top also. So, cracking, either fatigue or other type of cracking, is a major problem. Also, rutting is one of the major failures of many bituminous pavements in India because of the high temperature conditions. So, rutting or permanent deformation which occurs mostly in bituminous mixes if they are thick at high temperatures, or also it can of course also occur in other layers starting from subgrade, subbase, base, and which then gets reflected onto the surface. But of course, in this lesson we were concerned about the failures that are occurring in bituminous layer. So, we were concerned about the rutting that is occurring in bituminous layer. Other types of failures are bleeding that is seen on the surface because of the presence of excessive bitumen on surface, because of very little air void that was present, secondary compaction. So, bitumen coming to the top, that was another failure that we have seen. Similarly, these 3 or 4 types of failures can lead to secondary types of failures also. How to draw FHWA 0.45 chart for 19 millimeter nominal maximum aggregate size. FHWA chart makes use of 0.45 rule for finding out the percentage to be passing through a particular sieve size if we know what is the maximum size of aggregate that we are referring to. For example, in this case, if 13.2 is the maximum nominal size, then we take a convenient length of x axis and also convenient length for y axis. Y axis will be percentage passing 0 to 100. Then let us join this line. Then on this, if you want to try identify, let us say 2.36 millimeter size. So, we calculate what is the percentage to be passing through 2.36. So, we will calculate 2.36 divided by 13.2 to the power 0.45 into 100. So, we will identify that percentage here and then locate 2.36 here. So, on this any given gradation can be plotted, and this is the densest gradation, then any gradation can be compared to the densest gradation. The last question was how to check aggregate gradations for possibility of tender mix formation. This can be identified by checking whether a given gradation has got has a deviation of more than 3% from a line which connects origin to 4.75 millimeter sieve size. So, if a gradation has got deviation by more than 3%, that is considered to be leading to a tender mix.